Welcome back to Physics Fundamentals. In this video, I'm going to be talking about matter and density. You should at least be somewhat familiar with the terminology of matter. The classic definition tells us that matter is anything which takes up space and has mass. All right, so if something takes up space, we can measure the space that the thing takes up as a volume. Matter has a volume. If it does not have a volume, if you cannot define volume for it, it is not matter. Now, sometimes that's a little bit tricky, right? This sheet of paper is thin enough that if I hold it just wrong, it completely disappears. Right? Choosing to hold a yellow piece of paper up in front of a green screen, probably not the best idea, but that's all I happen to have on hand. Right? So the thickness of a piece of paper is almost immeasurable, but the key word there is almost. Right? One sheet of paper seems infinitely thin, but if you get a ream of paper, right, a stack of 500 sheets, all of a sudden that has an appreciable thickness. So clearly, each sheet is taking up some space, and when you stack them together, they take up a lot of space. All right, so matter takes up space. It has volume. Matter has mass. And those two ideas are going to be kind of the feature of what we're looking at throughout today's lesson. In a chemistry class, they often go into a lot of detail about classifying matter. I'm going to kind of mention quickly. Right. Elements are the most basic types of matter that exist in our world. Compounds are comprised of multiple different kinds of elements. At the smallest bit, an element is made up of atoms. And of course, atoms themselves are made up of protons, neutrons, and electrons. But protons, neutrons, and electrons aren't interesting in the scale that we can experience, at least in this sense, right? An atom intrinsically is the element. If you have one atom, if you have 100 atoms, if you have 1 billion atoms, it doesn't matter. It's still the same thing. If you have a pile of neutrons, then you have something that is very different from that matter. So it's the collection of protons, neutrons, and electrons in an atom that makes the element what it is. If you combine several atoms together, you get something that is called a molecule. So, classic example, water is the molecule H2O. It is comprised of 2 hydrogen atoms and 1 oxygen atom. All right, I could go into a lot more detail about that, but this is not a chemistry course, so just that basic surface understanding of what we're talking about, what all this vocabulary is referencing, is more than good enough for our purposes this semester. All right, so let's clear that out of the way. When we are classifying matter in our world, generally speaking, we're going to classify it between solids, liquids, and gases. If you happen to be well read, you may have also come across this idea of a plasma, which is a 4th state of matter. Plasmas are an exotic form of matter that exists in stars and very rarely anywhere else. I don't have the means of showing you something that is made of a plasma in this course, so we're going to kind of ignore it and pretend it doesn't exist for now. If you continue on in your study of physics, it might be something that becomes useful in a future course. All right. But generally speaking, a solid, a liquid, or a gas is a description of how the molecules or atoms that make up the matter are grouped together. In a solid, you typically have atoms that are very closely spaced to each other. In a liquid, the molecules or the atoms are still fairly closely spaced with each other, but they have a little bit of flexibility. So one atom or one molecule might move around within the material where that doesn't happen in a solid. Right? That property allows a liquid to fill a vessel. Right? If you have a tall, skinny glass of water and you pour that water into a bowl, it will not remain tall and skinny. It will flatten out and it will fill the bowl instead. This is something you experience every day of your life, but probably don't often think about. A gas is even further distributed still. Right? Gas molecules tend to be very far apart from each other, and they tend to be moving and colliding with each other and bouncing all over the place all the time. Before I go too much further, I do want to mention about a gas. Even though we depict it like this with, these molecules or these atoms very far apart, I want you to think about a region, about shoulder width and maybe cube, about your shoulder width apart. Within that region of the gas, there's not just a handful of molecules. There's not just millions of molecules. That's behind my head. Let's put it up here where you can actually see it. There's on the order of 10 to the 23 molecules in the air, right here. That's a number that we will come back up to later on. If you've ever taken a course in chemistry, you might be familiar with the term Avogadro's number, which is some digits in front multiplied by 10 to the 23rd power. And that's a ludicrously large number, right? Things that are 10 to the 23rd power are not things that we come across in our day-to-day lives. And so I'm not going to try right now to give you some understanding of how big that number is, except to say it is beyond common everyday understanding. You have to strive to get there. All right. If you continue on in your study of the sciences, you will get there. We'll play around with that in many courses, in physics, in chemistry, even every now and then in biology. But for our purposes, just understanding that atoms and molecules are unfathomably small is good enough. All right. So as you're looking at a solid, as you're looking at a liquid, as you're looking at a gas, you notice that the molecules start to spread further apart. A property that you are probably familiar with is the idea of freezing, thawing, and boiling. Right? If you take liquid water and you put it in the freezer, it suddenly turns into solid ice. If you take liquid water and you put it on the stove, you see vapors rising off as the water boils. And eventually, your kettle of water will run empty if you keep it boiling long enough. If you keep going long enough, the kettle itself will start to melt. Hopefully, you have never experienced that. I've seen it happen once in my life, and I would like to never see it again. So there's a transition between these states, and some of it is kind of rapid. It happens very quickly, but at the same time, it's somewhat gradual. And so these atoms or molecules can move closer together or further apart. Sometimes they get locked into places, like with ice, right? The molecules that make up water ice tend to be very rigidly interlocked with each other in crystal patterns. And water has a weird tendency where these crystals cause the water to actually spread out, cause the molecules to spread out a little bit compared to when it's liquid and they're able to move around with respect to each other. That's not something you see in, honestly, I don't think anything else, but as soon as I say nothing else, somebody will find something else somewhere. But it's not something you see very often in the world. In general, the way we describe how closely packed these molecules are to each other is the density of the material. And even this definition of density is kind of tricky. We talked briefly when we were discussing units of measure that there's this idea in the metric system, in the SI units, of mass, which is an intrinsic property of the material, which we measure in kilograms. In the US customary system, and formerly in the imperial system, we didn't use mass, we used the weight, generally in pounds. There is a link between them, but the weight of an object depends on gravity where you are. And for the most part, when you're on the surface of Earth, gravity is more or less the same. If you go down into a deep valley or up to the top of a mountain, gravity will change slightly. If you escape into an airplane, gravity will change slightly more. And of course, if you escape into a rocket, you will experience a feeling of weightlessness where gravity seems to cease to exist. We will explore how all of that works later on in the course, but for right now, just understanding that intrinsically, the mass in kilograms and the weight in pounds are linked to each other, but they're not measuring the same thing, right? Mass is measuring something intrinsic about the material. Weight is measuring how gravity affects the material. Your weight on Earth, your weight in space, your weight on the moon, your weight on Mars would all be different. But one of the issues with the measurement of mass or weight is that it plays on too many things, right? The type of material that you're dealing with will affect how heavy the result is. Aluminum is much lighter than steel. Styrofoam is much lighter than wood. But the shape of the object also plays a part. If you make a larger object, it is going to have more mass. It's going to be heavier. It's going to have more weight. If you make a lighter object or a smaller object, it will have less. And so if we want to compare just the property of the material, what makes some materials heavier or lighter, we want to get rid of the shape causing an issue. And to do that, we will divide by the volume of the object. For mass, in kilograms in the SI system, the volume of an object is in cubic meters for a solid object or in liters for a liquid object, but generally speaking, those are a conversion factor of parts. We won't worry about it. Likewise, in the US customary system, when we're dealing with pounds, you could do pounds per gallon for a liquid or pounds per cubic foot for a solid. We're not going to do that much work with the US customary system in this course, but I think it's something interesting that's worth discussing. All right, let me get my head out of the way now And let's go through a practice calculation, or maybe a couple. Aluminum at room temperature has a density of 2,700 kilograms per cubic meter. Determine the mass of a block of aluminum measuring 8.5 centimeters by 6.90 centimeters by 4.20 centimeters. All right, so let's set this up. I don't think I've written the formula down yet, but I've mentioned that a density is a mass divided by a volume. So there's our formula. That gives us three variables, d, m, and v. The density in question is given to us. It is 2,700 kilograms per cubic meter. We are asked to determine the mass, so I'll put a nice big question mark here next to the letter m. The volume we will need in order to solve this problem. But we don't know the volume. We know information about the block of aluminum. And while the problem doesn't give us a picture, it does kind of talk about the aluminum in such a way that I feel pretty confident in saying that it is in the shape of a rectangular prism. So we can write down the formula for the volume of a rectangular prism. It's length times width times height. And we can write down those variables, L, W, and H. Right. The next thing that I notice in this problem is that my density is in kilograms per cubic meter, but my length, my width, and my height are all given in centimeters. Having mixed units can be problematic. So in order to avoid any issues with that, I'm going to go ahead right now and do some conversions. I'm going to move this over a little bit. The wonders of working on a digital tablet is I can give myself a little bit more space whenever I need it. Right. But that length of 8.50 centimeters in meters, that's going to be 0.0850. That width, which is 6.90 centimeters, is going to be 0.0690 meters, and then the height will be 0.0420 meters. So I've given my length, my width, and my height in meters this way. All of my units, I am now confident, are going to work out. All right. Now we can take that information and plug it in, right? To find the mass, the other variables in the formula are density and volume. We know the density, we don't know the volume. And so even though we are going to be working with it, we don't have it just yet. That was supposed to be a pointer, not a drawing. All right, anyway. That tells us that the first thing we need to do is use our volume formula and just multiply our length times our width times our height. All right, my calculator is very happy to do this. It gives me a small enough number that I'm tempted to leave it in scientific notation. I'll also notice that all of my measurements had 3 significant digits, So I want this result to have 3 significant digits as well. I'll round it to 2.46 times 10 to the negative 4th cubic meters. Right? If you wanted to write it out as a decimal, it would be 0.000246. I'm sorry, I think I misread the number of zeros. 0.000246 cubic meters. Right? That's a lot of zeros. That's just enough zeros that I'm starting to think scientific notation, not standard notation. But if you're happier writing it in standard notation, there's nothing wrong with that. Right? In any event, we now have that volume. Our other formula was given to us as density is mass over volume. If I swap left and right side of this formula, mass over volume is equal to density, and then multiply both sides by volume, and the mass is the density times the volume. Right? I don't want to keep going down the page because I want all of the data that's at the top of the screen to stay there. So let's just draw a squiggly line here so that I can move over a little bit. Right. I'm working on a landscape screen, so I have a lot of room left to write and not a lot of room up and down. You're probably not working in that orientation, so you have a lot more room to go down the page. All right. But my density was given to me as 2,700 kilograms per cubic meter. My volume I calculated as 2.46 times 10 to the negative 4 cubic meters. And when I set that up, the cubic meters down here and the cubic meters up here are going to cancel each other out, leaving me with units of kilograms, which is exactly what I hoped to find. And then when I multiply that number by 2,700, I get 0.6651, but my density, 2,700, only had 2 significant digits, so that's what I'm going to use as my limiting factor when I round. And I don't know, maybe I should round that up. Looking ahead, don't just start copying digits. 0.67 kilograms is what I get as the density of this object. All right, so one new formula that we get to play around with, and one of the things I like about this formula is it also immediately introduces us to this kind of problem solving where you have to use 2 formulas in order to solve the problem. All right, let's take a look at one other, which is closer to what you see in a lab. This one closer to what you see in manufacturing, right? If you're the engineer and you are looking for how much is this object going to weigh, is the structure I'm building going to be able to support it? Those sorts of calculations are what you want to do. If you're exploring the property of the material, you might approach it a little bit differently. So for example, the mass of a spherical casting of an unknown metal alloy is 1.20 kilograms. If the radius of the sphere is 4.00 centimeters, what is the density of this alloy? Right, so in this case, we are exploring a material we have not seen before. We take this material, we cast it at a very precise size, and we then measure it. We measure the mass by putting it on a balance. We measure the radius by using calipers. Okay, we probably found the diameter and then divided by 2 to get the radius. But in any event, we now know that we're dealing with this material. So we know that density is mass over volume. And I'm going to go ahead and jump in right away. We know we're dealing with a sphere. And a sphere has a volume given by 4/3 pi r cubed. So our variables in this case are d, m, v, and little r. The mass is given to us. It is 1.20 kilograms. The radius is given to us. It's 4.00 centimeters. Just like in the last problem, though, it's going to be a lot nicer if we have that radius in meters so that our density comes out in kilograms per cubic meter, which is the more common unit of measure. Knowing that radius, we can come over here my calculator is happy to tell me that if I take 4 divided by 3 times pi times 0.0400 to the third power, I get 2.68. Right? 4 is an exact value, 3 is an exact value. I used pi in my calculator, which has more digits than I care to think about. And then I'm left with just this measurement, which had 3 significant digits. So I round my result here to 3 significant digits. 2.68 times 10 to the negative 4. And my units were meters, which I raised to the third power, leaving me with meters cubed. Now that I have that volume, I can go to my other formula. Density is mass over volume. I know that my mass was 1.20 kilograms. I know that my volume was 2.68 times 10 to the negative 4 cubic meters. And when I ask my calculator to do that division, my calculator tells me that this is going to have a density of 4,480 kilograms per cubic meter. Once again, 3 significant digits here, 3 significant digits here. So I round my result to have 3 significant digits, even though if I look at my calculator, that's, decimal digits continuing until the end of the screen. All right. So there we have it. We have this new concept of density. Using density gives us a different approach for solving problems. We have to start mixing formulas together using all of the tools that we just developed of geometric formulas along with this new one, density is mass over volume. That's all I have for you in this video. As always, thank you for joining me, and I'll see you next time.